Okay. Yeah.
All right, our next speaker in this session is Braden McDonald. He comes to us from North Carolina State University. I hope you had a good drive. And he's going to tell us how we can do periodic real-time tasks using OpenMP.
Yes. So, well, that's the first slide. It's introductions, which just been done. So we can begin. Yes. So short overview on my field in real-time systems. So real-time systems are computer systems subject to timing constraints. Very often these are cyber-physical, just computer systems that have some kind of physical component. There we go. Yes. Okay. Yes. Cyber-physical systems, computer systems, some kind of physical component, increasingly prevalent, often safety critical situations, vehicle electronic control units, or increasingly just vehicle control in general, with as much has been going on in autonomous driving. And with this was also come an increasing desire for multi-core systems, just to take advantage of the performance and like compute power increase. So with real-time systems being subject to timing constraints, and often timing constraints that can't necessarily be designed out in software. For example, you have a car moving at 60 miles an hour, then that's in 1 second, 88 feet. So the compute time has a physical cost in how far the vehicle moves. So you can't necessarily get away from those timing constraints in all cases. So predictability of execution time is often extraordinarily important. In general parallel system stuff, leveraging multi-core architectures for performance improvements, and of course the open problem of synchronizing between different tasks. And it's difficult to combine these two competing requirements. There's a lot of frameworks that exist for parallel, OpenMP being a major one, but most either ignore or just treat softly real-time guarantees. So the focus of my work today is, well, the focus of my work in general has been creating tools for real-time system development, mostly ease of development or verifiability. In this case, OpenMP-RT for real-time applications in OpenMP. So yeah, a framework for creating parallel real-time tasks running periodically, supporting both coarse and fine-grained parallelism. In this case, what we want is periodic real-time tasks running in parallel, so multiple tasks, as well as at the same time, those tasks being able to subdivide and run something in parallel, like in our sample implementation, some kind of parallel for. And then implementing synchronization method for communication across these real-time task barriers. And so here we have 3 pragmas, one to delineate real-time task, the RT task, and then 2 for reading and writing for communication between the RT tasks. So yeah, the design is based around the RT task concept. Construct is related to a single periodic real-time task. So each RT task represents one real-time task, and then leveraging the kernel scheduler for real-time guarantees. In our implementation, we focus specifically on Linux because with the preempt-RT part of the scheduler, we're able to get both, actually 2 different real-time scheduling methods, either static priority ones with a delineated priority and rank hierarchy, and then above that, earliest deadline first tasks, and a concept for OpenMP-RT has been getting coexistence between EDF and static priority. In a lot of systems, it's only one or the other, so we're pretty happy to be able to get both, with obviously all EDF tasks existing above the static priority band. And then per priority thread pools, in this implementation, for communication across the RT task barrier. We looked at lock-free. I'll go into that future slide. And that's also, that was also for allowing these multiple scheduling paradigms to coexist. There's also lower priority non-real-time processes. We're not really concerned with how those are scheduled, but they were thrown in some of our test cases for communication. The example for that might be some kind of wireless communication to download information for an autonomous vehicle. Actual example for what the RT task construct looks like in the code. So an RT task is associated with a single dedicated real-time thread. This is the one runs periodically, since all RT tasks represent specifically periodic tasks rather than ad hoc or sporadically run tasks. And that's when I mentioned the coarse-grained parallelism for OpenMP-RT, this is for getting individual RT tasks running in parallel periodically. That's the coarse-grained part of this. So fine-grained parallelism within an RT task is handled. In this implementation, we've only gotten support for either parallel for or the OMP task pragmas, are the ones haven't, it's an implementation issue actually getting the rest of that to work in this case. For fine-grained parallelism though, so the per priority thread pools exist mostly so that when an RT task mostly so that there's not resource contention for existing threads to pull in for a OMP parallel section pulled in by, there's not a contention between RT tasks of different priorities pulling from the same thread pool. So by guaranteeing the thread pool is per priority, we can always guarantee that, or it's easier to guarantee that RT tasks have the available threads to pull from when they want to bifurcate into fine-grained parallelism. Short thing. So in Linux, this is an example for an EDF earliest deadline first periodic task, just running it entirely through the native required pthread calls in Linux. So you've got 23 lines to actually run it periodically and 8 lines to actually get the pthread with pthread launch. And this is without any error checking or anything to see if that's actually supported in the version of Linux you're running in. So this is ignoring any of that. This is the bare minimum. And this isn't removed, but it's in the OpenMP-RT implementation moved into the OpenMP runtime. So it's handled for you, and then that way error checking can be put in there, and so it doesn't bloat that line cost. So an example for the thread pools. So with RT tasks, this is for the static priority ones, RT tasks running at a given priority level will pull from a shared thread pool for their intra-task, their fine-grained parallelism. This is an example in just a 4-core situation of just pulling from unassigned threads, assuming that red and blue there have the same priority. And then an example of, you'll note that the cores, even when not used, have already been assigned in that diagram, and that's because an example of something we want to avoid, which I'll go into how we avoid this in the next slide, is this case where the shared cores, we can't necessarily guarantee either one of these tasks will actually be able to express in a given job cycle, be able to express the fine-grained parallelism that it wants. And if it can't, then that can bloat the execution time massively. I mean, in this case, it might not seem, because red went from, in the desired case, running 2 threads to running 1 thread. But I mean, if you had more cores in a bigger situation, this could get very bad. You'd go from 8 threads down to 1. So we need a clear way to indicate the locality of tasks, to kind of partition the set of cores. So what we've done here is the integration of a configuration file that actually contains all of the information for all the RT tasks in the compiled program. This is passed in at compile time along with the actual C code representing or the C code for the program, the system. So this includes the scheduling information for a real-time task, period, deadline, phase, priority, and scheduling policy. Obviously, if your scheduling policy is earliest deadline first, your priority doesn't matter, it can be ignored. And similarly, in many cases, and you'll see this in the experimentations, that phase can be 0 and deadline can be just the same as period, but we do allow them to be different, because that's required in some systems. And this also allows us to identify what dependencies, the dependency variables that will be used for communication across RT tasks, and pre-allocate the data structures required to handle and protect those variables in when we have the coarse grain parallelism between RT tasks. And so this is the sample configuration file for one of the experiments that we'll go into in the results. Apologies, that's the same slide in an earlier version that I thought I had set non-visible. So it can be ignored. So this is just a short explanation what I said about the configuration, or previously the configuration file. So we have the application code in the configuration file passed into, in our case, the LVM compiler. This is the one we actually used. That contains a modified OpenMP runtime and some modifications to client to support the new Pragmas. And then get the binary executable back out that has the automatically generated code as well as references to the runtime. So regarding the block-free inter-task communication frameworks for communication across between RT tasks, two methods are proposed. We analyze both of them. We call them retry and double buffer based. These are implemented purely through atomic primitives. And then so looking first at the retry sync. So with retry, since we delineate the dependency variables already in the configuration file, this can be the structures for this can be created or can be defined at compile time. So for in the retry synchronization, I will note that for our implementation, switching between, we don't support both retry and double buffer. There's no way to indicate that. We just have separate versions of or separate versions of OpenMP-RT, one with retry, one with double buffer. That's, yes, for retry synchronization, there's 2 timestamp registers associated with each just block of data. Whatever size block of data is defined for the dependency. And on a write, all we have to do is update the top timestamp, write the data, and then update the bottom timestamp with the same value. So we don't need it. We don't want it to be a different value of the timestamp when it finished, just the same one as the top. And what we can do then is on a read or when a write comes in, check if the timestamps are equal. If they're not equal, there's a write going on, so back off, retry. And you can do this if you're a reader or a writer. And if you're a reader and they match and you read, you just check again at the end. Do they match the previously observed ones? And if they don't, you know that your read was invalidated, retry. What we do, there's a user configurable maximum number of retries before it kicks back and says that the read operation failed or the write operation failed. And then how that's handled is up to the application code. I will note that as these are periodic tasks that are communicating, careful analysis of the schedule, the hyperperiod, which is the point at which the behavior of the system repeats in terms of what tasks are running at what times. It is possible to determine, well, even if it fails this many, or even if it fails on one particular job cycle, I can guarantee it'll succeed at the second job cycle, and then write your application code to work around the fact that you don't actually know if you have this cycle's data or one cycle previous's data, or however many cycles you think you can accept. Double buffer is similar, but reduces the number of invalidations we get. In this case, for every dependency variable, there's just two slots for it, just two segments of data. And then a single pointer for it, and a small write flag. And all that needs to be done then is whichever one is pointed to is readable, and thus by definition we assume the other one is writable, or could be writable. So then on a write, all the writer has to do is set the flag to prevent write collisions, so multiple writers don't try. And well, check the write flag first. Then if it's not already set the write flag, write the data, and at the end, switch the pointer, which just swaps which buffer is readable and writable. Reader, then all it has to do is go read the current, read whichever buffer is currently being pointed to, and at the end, check. And if it's been updated, retry. If it hasn't been, good, the read succeeded. So this does reduce read invalidates slightly, since a writer that comes in but doesn't finish writing before the reader finishes reading won't invalidate the reader won't invalidate the reader. So for experimental analysis, two sets of experiments. One using synthetic task sets built just auto-assembled based on the Barcelona OpenMP task set and the EPCC benchmarks. These were just used to assemble just component real-time tasks, each RT task containing just one of these selected tasks. With these, worst case execution has were just gotten experimentally for the system that was being used. And then just randomly generated applications. So, and the second experimental set more recently was derived from the Hydro benchmark, which is a fluid dynamic simulation, which we picked just for the dependencies between the actual domain or subdomain calculations. And this was just to compare the retry double buffer with the control version. So for the bots and EPCC synthetic tasks, so this is the utilization stress test. So we could show complete avoidance of deadline misses for the synthetic tasks at below 95% utilization. I'll note that utilization was adjusted in this case just by artificially inflating just artificially inflating the compute time for the task without needing to actually change the real-time parameters of the task set. So similar stress test for the Hydro benchmark. This is comparing with the communication using the retry and the double buffer methods, largely similar results in that case, with a control version just using standard OpenMP for the fine-grained parallelism and just preempt RT pthread calls instead of the OpenMP-RT RT task pragmas. So this goes back to the bots and EPCC synthetic task benchmarks. So compared to a lock-based method, we see lower increases in average response times as total utilization increases for the retry methods compared to lock-based. And so here we're looking at communication either between real-time tasks or across the real-time barrier, communicating out towards non-real-time tasks. We still see improvements, even in cases where we're communicating with non-real-time tasks. I don't know how much time I have left, so, okay. So yeah, so in this case, looking at just the number of failed reads for all three cases, communicating between real-time tasks, communicating from real-time out to non-real-time, and then communicating non-real-time information or non-real-time tasks communicating up to a real-time RT task. There's minimal variation between these sets, in this case, the ratio of the period of the producer to the period of the consumer. Since what invalidates a read is a write coming in at the same time, or while the read is still executing. So in this case, this was just looking at a comparison of behaviors of readers versus writers in the hydro benchmark set in the utilization stress tests from previous, from the table previously. And what we see here is that the response time increases, which were responsible for the deadline misses that were observed at very high utilizations, are entirely in read requests. There's not really a corresponding increase in writer response time. And that's because writers are invalidated much less frequently than reads, just due to the nature of the buffer and retry. So, and this is the last one. Lines of code are not one-to-one complexity, but since there was a slide previously, I figured I would put in short measure of the percentage decrease in the length of the code base. And again, this is not measuring code that's removed entirely, it's not executing, just things that have been kicked over to the OpenMP runtime or can be standardized and where the programmer doesn't need to worry about it. And so that is, that's the end here. So I guess I can go on for questions if anyone has any.
Thank you. You have any questions for our speaker? Okay, I have one. So the way you're configuring your task is that you have some pragmas in the code and you have a separate file that contains like runtime and things like this.
Yes.
Is that the common thing in OpenMP runtimes to have these separate?
Not particularly. Not particularly. It was in this case mostly done to handle that pre-allocation of it's called that pre-allocation of space for dependencies that would be very difficult to do if they're just referenced for the first time somewhere in the code. Okay.
Do you have a question from the room or from the online audience?
I have a question. I'm not from the RT domain, so I don't know if it makes sense. What happens if a task doesn't make it to the deadline? The time passes.
So in theory, timeliness is considered part of correctness. So that's essentially equivalent to a task just computing something wrong. In real-time systems, how that is handled is system dependent, whether you go into a safe mode or you deprioritize the task or just crash. You don't want to do that, but I mean, it is essentially the task is failing. So depending on the precise system, you might handle it in a number of different ways. I mean, fault tolerance is kind of an open problem.
I just want to understand the idea of the thread pool. So in some early part of the code, I do set none threads to n, but then later in the code, I use less than n threads, and the difference is what you call the thread pool.
So it's not so much the difference, but the thread pool just contains the waiting threads. So if you use less than that, there's the ones you didn't use are still in the pool, presumably available. Like in this case, blue it only uses one, so there's another one available for red. Now in this case, we only have four, or I'm only showing 4 cores. So I guess those other threads aren't really necessary. But in theory, if there were more cores, there would be, you know, there's 2 threads available for work and
So
fine grained
extra
stuff.
threads available in the team, but you use less than those, and they stay in the thread pool.
Yeah,
Okay, thank you.
they just, yeah, they stay available in theory if
Thank you.
needed later.
All right, any last question for the speaker?
Maybe I should comment on this one over here, since I'm involved in this. So the pools are also a little bit different in that maybe you can explain that pools have priorities associated. There's multiple pools.
Yes, so
Not each pool is created equal.
yeah, in our case, yeah, these are per priority thread pools, which just exist because in Linux, taking a thread and then promoting it up to your priority is computationally expensive and
How do you
it's easy.
assign priority to a thread?
Hmm?
How do you assign a priority to a thread?
I mean, that's handled in the scheduler when the thread is created. And that's, so in our case, the thread pools are per priority. So when they're created created at that priority, but then there's not really anything to do with them yet until they're assigned to a job. But the RT task is pulling only from the pool that's already pre-created at its priority.
And maybe just to clarify, this is different between opportunity and performance and safety and being really conservative about this. So you can't promote lower level priority threads to higher level because there may be a lag in the activation at the higher priority level. You already have to have them at the higher priority level ready. So we can go into this in detail, but that's a scheduling problem.
I'm not interested in changing the priority, just interested in utility.
Right, that's why we do it. And the other part that's maybe also interesting, if you go back to the specification, which is unusual to have a specification file, even though web PTAs, you may do that in OpenMP as well, it's being discussed. But the other reason we have this one is you're interested in proving correctness of real-time systems. So in this case, you would take a task specification, actually show the schedule on the amount of cores that you have, given these parameters.
Yeah.
So this is something that you get on the side.
Yeah, so like Dr. Mueller said, if I give you just this, I don't give you my code, all I give you is my configuration file, you can show that this would be schedulable, or this would be schedulable on the system, or it wouldn't be, and I don't need to look at your code, I look at this and I know there's an issue. I'll also note that one of the things in the configuration file does define the number of threads that we expect, that an RT task is going to be allowed to use, and that's priority. So
So
from
those 5 threads get priority 10.
yes, when the program is created, it will make, yeah, it will make, let's see, yeah, it will make 5 threads with priority 10. I could, in theory, if I wanted to have some other task named domain 4 that's also at priority 10 that takes 3 threads, you'd want to create a pool of 8.
Maybe just to put it into the big context over here, the workshop, but also OpenMP specification context, it's an opportunity for OpenMP to be adopted by other domains. So look at what's happening with machine learning and autonomous systems. Right now, nobody's using OpenMP or even considering it, but in part, they also have a problem with predictability, and it would simplify the interface to make things predictable in a context that essentially is being used in autonomous driving. So Tesla is using Linux inside NVIDIA GPUs, but they have their own custom solutions today.
All right, let us thank our speaker again.